linking. So everything that you mentioned here, we will record it and we will be sending it to all the people in the hackathon as a recording in YouTube, so they are able to use it as a reference for the privacy track that StarkWare is sponsoring. Well, StarkWare and two other companies. We also have the Fat Solutions. I think you know them, right? Fat Solutions.
Yep.
Fat Solutions and WhatsApp. So we have a big privacy track thanks to you guys, WhatsApp and Fat Solutions. So yes, I will be sending all the recordings. Any repo or any message that you send here in the chat or send me in Telegram or in Slack, whatever, I will be sharing them to them also. So we have a
Mhm.
full sources that will include this that you will be sending or that you will be using today. All of that will go into the resource library that we have. Yeah, okay. So everyone who is in here, please use the chat or use the question and answers tab. I will be giving you the questions, Michael. So don't worry about the chat. I will be reading the questions, try to answer myself as much as possible, and giving to you the next, giving the other questions to you. Also, I'll be checking YouTube to see if there is any other question that I need to tell you about. And yes, so I think any doubt, Michael? Otherwise, we can start. Huh?
Yeah, let's start.
Perfect. Okay. Thank you.
Sounds good. All right. Just a second.
While Michael shares the screen, thank you everyone for coming. By the way, sorry, Michael, you were saying something.
No. All good. Okay. Yeah, let's start from the very beginning. So, hi everyone. Thanks for joining. Michael from StarkWare Exploration team, and I wanted to share some slides and a demo on how to build privacy apps on Starknet. So I believe that there was already an introduction last week by
Solutions.
Fat Solutions. On that, so we will have a certain overlap, but I will be focusing more on Noir specifically, and also maybe share some ideas on what you could build with Noir, Garaga, and some other tooling that might be exciting. So first of all, just to recap and give you some mental model, I wanted to get back to kind of definition of the privacy preserving application. So what is it, and how do we think about it? And if we start with the like from the very beginning, like how blockchains work and how layer one chains work. So the mental model is if you wanted to verify that a certain program, let's denote it as P, has executed correctly, meaning that it produced a certain state with a certain inputs and the resulting outputs. In order to verify that, all the nodes in the network should re-execute the same program with the same input state and with the same arguments, and afterwards compare the results, and if they reach the consensus, like everything is great. Okay, so this is how the layer one chains work. So the next step is that is great, right? So the obvious problem is the scalability, right? So the more nodes you have, so the more computation, the more redundant computation you need to do. And this is not good, okay? So the next step is instead of re-executing the same program multiple times, we execute it once and we produce a proof called also validity proof that a certain program actually uh, produced a certain state given a certain inputs and the certain input states. And after that, we can verify this proof on the underlying layer one. And again, so the verification itself has to be done multiple times on all the nodes to achieve the consensus, but it is reasonably cheap and small and like uh, much smaller than the computation that we have proved. Okay, now uh, in this scheme, right? So everything is cool, right? So we solve the problem of scalability, but we still like for certain programs, right? We might want to hide the input that we used with the specific program, and for that purpose, we used a zero knowledge program or zero knowledge circuit, and the model in this case is roughly as follows. We have a program, we have inputs. Now we have both public inputs that are available for every, like all the observers, and we also have private inputs that are not known to publicly known. So these are only the inputs that we know at the moment of proving. And now we also execute the program and we produce the proof, but now it's not only it is a validity proof, but it's also a zero knowledge proof, meaning that we hide the information, part of the information that we provided as the input to our program. Okay, and so the like afterwards, so the workflow is the same. So we verify the proof. If the proof is correct, so we like either achieve consensus, or if like we operate like already on layer two. So now we have certain like a chain where we first produce the zero knowledge proof of our program, then we aggregate multiple verifications of such proofs and create another validity proof of this verification. And lastly, we settle this proof on underlying layer one, right? So this is roughly the scheme of the ZK rollup. It's how Aztec is going to work and like hopefully others. And the idea here is that the first part is something that is done on the client side, right? Because the only way to, I mean, not the only way, but kind of like the most straightforward way to ensure your private inputs are not exposed is to do any sort of computation with them locally, right? So without delegating to any other server. Okay. Afterwards, so everything can be done on the not necessarily trusted remote server, right? So the uh, transaction aggregation for the rollup, and then the submission to the layer one. So everything is happening kind of like outside of your private machine. So this is kind of like the mental model I really wanted you to have. And the next question we're asking ourselves, what is the privacy preserving application? Uh, it's roughly two things. So first is the program itself, right? The zero knowledge circuits, like something that we just mentioned. But uh, like another part, which is also very important and kind of crucial, is the state, right? So if we wanted to do something more or less meaningful, so we need a state. And it's like since we're talking about privacy preserved applications, this automatically means that the state has also to be private. And that's where all the problems are, usually with the private application. So here on this diagram, I have like a really high level scheme of this interaction between the uh, client-side prover and the rollup where we do aggregate transactions, right? So typically how it's done is your private applications consist of two parts. So it's the client-side part that is executed on the client, and it typically includes ZK circuit, right? So this private program that you're running. So you have the executor and prover for a specific proving scheme. You also have the application-specific indexer for your state and certain infra for management the keys. So we will get back to that a bit later. Now, on the kind of like on-chain part, the smart contract that lives on the rollup where you verify your zero knowledge proof typically consists of the verifier itself, right? So the smart contract, like the program that verifies the zero knowledge proof, you also typically have some business logic, right? So where depending on the outcome of the verification, you do, I don't know, like do the payments or like unlock some funds, etc. You also have and you also have a certain part that is responsible for managing the state. So at the very least, you have something that's called state commitments, or you might heard also the term nullifiers. So this is just like very like roughly, it's the hashes of the data that you use inside your zero knowledge circuit. And in some cases, you also might want to store your private state on chain. And of course, to keep it private, you need to encrypt that, right? Uh, so, right, again, here, like the white boxes are kind of the part of your private application that is stateless, okay? And in some cases, so this is enough. Typical example is ZK login, like where you need to just verify the proof that it attests that you own certain email address or Google authentication token, things like that. And just by verifying the proof, you don't need to store any data on chain. You just need to verify the proof, and this acts as a key that opens like the door, and you can afterwards get some permission and do something with the public data. But in other cases, such as private payments or private DeFi, you still need to you need to maintain the state on chain. And that is like much more involved because not only you have to just keep the encrypted blobs on chain, but you also have to index this state on the client side, which can be like quite non straightforward. You have to manage the keys, and typically you have multiple keys, viewing keys, encrypting keys, and so on. I need to make sure that you do this reliably so that so that your client, your users won't end up in a situation where they lost their keys and, cannot decrypt their encrypted states and so on and so on. So yeah, this is important. Now, okay, so here we talked a bit about the program part of the zero knowledge application and the state. Now, how do we do that on Starknet nowadays? So for the client side part, right? So for the part where we write our zero circuits, where we do some things with the private data that we do not reveal to the public. So the recommended way to do that is to use the Noir language. What is Noir? So Noir is the domain-specific language for privacy preserving applications, right? It's inspired by Rust, and it feels a lot like Rust and has similar package management. It also has a really convenient internal representation that allows multiple proven backends. But for like most of the time, so and like we in particular, so we use a specific flavor of the backend that is developed by Aztec. Uh,
Is it,
for
sorry,
like
Michael, sorry to
yeah,
interrupt you, Michael. There's a question. Is it similar to Cairo? I mean, if you know Cairo, the transition to Noir is very difficult. What do you say?
I would say that in some sense, yes. So there are like some similarities. So I mean, it's not that you can, translate a program from Cairo to Noir easily. Maybe like for some simple programs, yes, but this is not generally the true. But yeah, like overall, so it's like really Rust-like. You just need to uh, know some, language specifics because it's still domain-specific language. So for instance, um, what are the difference? Like in Cairo, and both in Cairo and Noir, you have field element type, right? It's kind of like the core type that is it depends on the underlying math that is used for in the proving system, and you have different types in Caro and Noir. So in Caro we have a file like 252. In Noir it's like different different fields, and so yeah, that might break some assumptions about the programs.
Hmm.
Some assumptions about the underlying type system, like in case if you want to, I don't know, pack some data into the field element. So there might be issues,
Okay.
but yeah.
Oh, no, sorry,
So
sorry. Okay.
no worries. Okay. Now for the on-chain part of our privacy application, so we use Caro language because it's the language we write smart contracts on Starknet. So in general, so Caro, you can use Caro not only for smart contracts on Starknet, but just for generic programming. So you can write whatever in Caro and then prove it. And Caro is also really Rust-like, except for certain things that are different from standard Rust, just because in Cairo we have a slightly different memory model and a couple of other things. Uh, yeah, but so in general, so Cairo is a language that is really friendly to proving system, and it works particularly well with Starks. And this is the language that is used to write, as I said before, like for write smart contracts, but it also the language that Starknet's operating system is written in. It's kind of like the large program that aggregates multiple contract executions on Starknet to afterwards generate the proof that is then settled on Ethereum. Now, so privacy applications on Starknet is essentially combining those two technologies together. And the reason, so why this particular choice is on Starknet, we we can verify Noir proofs really efficiently thanks to the piece of technology called Garaga, which I will explain a little bit later. But also, there are a couple of features that are kind of unique in Starknet that allow more expressive privacy applications, which is, for instance, native account abstraction. Uh, that is a feature that kind of separates the transaction validation and execution. And there are a couple of use cases where you can let's say, verify zero knowledge proof even before transaction execution. So um, you can enable feeless like an experience without paying any fees, kind of like a paymaster, based on just verifying zero knowledge proofs at the stage of transaction validation. So this is pretty cool. And just in general, so in Starknet, the transaction fees are really low, and that allows a really great developer experience. Now, why? So this is why Starknet for the Noir. I think these days Noir provides the best experience for developers to write ZK circuits compared to other tool chains like Circum or like anything else you can find. And it's also really, really fast with the backend that stack is working on. So it's comparable to Circum on most benchmarks. The proof size is also pretty small. So it's much smaller than Stark's, and that makes it like really efficient in terms of the communication and also in terms of verification. And lastly, so Noir uses universal trusted setup. So if you know what it is, so roughly it like very high level, it means that you do not need to do some involved ceremony for every version of your circuits, which was the case for Circum Gross 16 instances that many teams used before. So yeah, overall, it's a win-win. It's kind of like the best of two worlds. The best zero knowledge toolkit and the best smart contract layer. And now I wanted to say a few words about the glue that kind of sits in between of two stacks. And as I mentioned before, so this is the piece of technology called Garaga. And that's actually three things in one. So first of all, it's the code generation tool. So it's the application that allows you to translate, to generate a smart contract based on your existing zero knowledge circuit in Noir, right? So you just feed your Noir code base to Garaga and it will output the ready-to-use smart contracts that would verify the proofs. So secondly, it's just the development kit for encoding the call data for interacting with this verifier contract, and it's available for Rust, for Python, and TypeScript. And lastly, it's just the Cairo library that allows you to do elliptic curve operations, to work with signature schemes, and just generally with the with circuits inside Cairo. So this is a really high-level scheme, how it works. So given your Noir program, you use Garaga to code generate to produce the Cairo code that you can later deploy on Starknet. And you do this once. And afterwards, every time you interact with your zero knowledge program, after like every time your user interacts with your zero knowledge program, on the client side, you generate the witness to the circuits, you produce the proof, you then encode the proof, again using Garaga, to obtain the call data for the verification contract. And lastly, you invoke the previously deployed smart verification smart contract on Starknet using the call data you produced with Garaga. So
Sorry,
this is,
Mike.
yeah,
Sorry, Michael. Can I ask you a couple questions here, please?
of course.
Yes. So, Michael, we have a question. Can you use Cairo for zero knowledge, for CK?
So currently, not really. So we will, yeah. So short questions, no. At some point, so we will enable that. Yeah, but right now the prover that works with Cairo is not ZK enabled. So it leaks certain bits of the inputs through the proof, which makes it, yeah. So you can achieve like kind of practical ZK with Cairo and the current prover using recursion. So it just makes it like hardly like almost impossible to extract the bits of the witness from the proof. But it's not statistical ZK, so it's not the same level of security that you get from Noir and Berthenberg prover.
Uh, Perfect. Thank you very much. And another question is, what you're mentioning right now, it means that you can write a whole layer one with Cairo, unrelated with the Starknet, right? Unrelated to Starknet.
Sorry.
Yes, let me see if my audio is correct. Just a second. So it says that you can write a whole layer one with Cairo related to Starknet,
You can write the whole layer one in Cairo. Um,
a
I
layer one
mean,
network.
I don't think so. Um, like layer one network. So typically, if you write a blockchain node, you have kind of like a multiple components, like the component responsible for the peer-to-peer networking, for state management, and just one layer is where you have your state transition function. So typically Cairo is used for this business logic for the state transition, but not for your networking state or and everything. So you cannot do that in Cairo right now.
Hmm,
So yeah, you cannot do layer one in Cairo. You can only do like a
perfect.
certain component of the layer one in Cairo.
All right, all right, all right. Okay, it was because the question here is I ask because you said you can use Cairo without the Starknet, right? You can.
Yeah, of course. Yeah,
Yeah.
yes, you
Yeah.
can use Carrot like outside, but
Mhm.
you use this for the programs that are uh, like if you ever used Rust with the no STD, like without the standard library and any like input output. So this is roughly the equivalent of Cairo. So you do not have
Hmm.
access to like periphery devices. uh, it's a almost like a pure function. So whatever you provide as an input, that's all you can access.
All right. Okay. Okay. And there's another question by Laura that says, okay, so Laura is asking, maybe we need a couple more minutes for Laura to figure out the question or questions. Laura, feel free to ask as many questions as you want. Okay. I think we can continue my call in the
Sure.
meantime. Yes.
Okay. Great. Okay. Just to recap, so Noir works really, really well with Starknet and vice versa. So the for the proven system that Garaga kind of uh, includes by default, we can verify zero knowledge proof on Starknet for like a couple of cents. So that's 2 magnitudes more efficient than on Ethereum and comparable with our other L2s. And yeah, something that I mentioned before, you can use Noir with account abstraction and the the limits that we have right now allow to verify the proof at the transaction validation stage. So basically before you charge the fees, and that allows you to do some interesting use cases. Uh, okay, now a couple of words about the current privacy landscape on Starknet, what we have right now and what we have in works. So the currently most of the efforts are focused on payments. And roughly, we can separate them into two groups. So the first is collectively called privacy pools. So you might probably be aware of the privacy pool project on Ethereum by the 0xBall team. So we will also have an instance of that on Starknet. And in a nutshell, so it's a mixed based design. So it's sort of like Tornado Cash, but the with built-in mechanism for compliance. So you can rely on things like proof of innocent and kind of generally like the main feature of the privacy pool is that it breaks links between deposits and withdrawals. So if you put some money in the pool and afterwards withdraw, so it's really hard being like an outside observer to create a connection between those two events. But you have to be like really careful, not nonetheless. So the making deposits and withdrawals is kind of core functionality provided by the pools. There are also extensions to that allows you to do some interesting stuff being within the pool, like just transferring tokens between the pool participants or accessing existing DeFi applications on Starknet. So this is sort of similar to how Railgun works. And so yeah, that's one group of solutions that is currently like either being already deployed or in works. So the second group is what we call confidential tokens, and this is a sort of a privacy solution that addresses a specific problem. So unlike privacy pools where we kind of hide everything about the about transactions, so it's not possible to trace who was the sender, what was the amount, like etc. So with the confidential tokens, the sender and receiver of the tokens are known. They're like still publicly visible. So the only thing that is hidden is the amount of transfer and the respective balances of the sender and receiver. And this is a slightly different cryptography and design of the solution. It relies on the partially homomorphic encryption. And again, so it also has a built-in mechanism for compliance in order to be able to de-anonymize certain transfers, like in case of the like authority requests or anything. And the upside of this approach is that it's quite lightweight in terms of the state management. So you don't have to do this involved indexing as you have to do for the pools. But the downside is that it's not immediately compatible with the existing DeFi application. So if you wanted to do kind of confidential swaps or confidential lending or borrowing, right? So you have to write such primitives that are implicitly compatible with the confidential tokens, and this is not straightforward thing to do. Now, what would be really interesting to see on Starknet, and what is now I think mostly in the exploration stage, is two things. I mean, there are more things. It's just like two things that I wanted to bring attention to. So first is the private trading. So again, it's the kind of custom privacy solution that solves specific problems. So not just the the ultimate privacy that would be the paradigm, but just we solve like a practical problem. And this problem is the hiding trading strategies, right? So now everything you do on chain is publicly visible, including what you trade and how you trade, like how you enter the position, how you liquidate position, like and so on. And hiding this particular information would be quite valuable for traders. So there are a lot of demand for this specific feature, and there are several companies that are trying to solve this problem. So, for instance, Silhouette for Hyperliquid, and I believe so couple like several more. So it will be quite cool if we have something on Starknet for extended, in particular. So this is a really cool direction to explore. And secondly, any DeFi primitive with the either partial or fully private shared state would be really, really cool to see. There are a couple of ways how you can achieve that. One approach is to use something that's called collaborative ZK. It's when you have, like, instead of one prover generating a proof for a specific program execution, you have multiple provers that form a network, and you split your private input between them so that your information remains private. So here you can use the tool chains provided by Tetseo. Specifically, I think they have something that's called Noir, collaborative Noir, and it should be compatible with Garaga as is, And it might be like, yeah, it would be really, really cool to see those two technologies work together. And yeah, lastly, so for privacy, so not for kind of enforcing the integrity, but just for privacy, it might be okay to use trusted execution environments to have encrypted order flow or encrypted order matching, things like that. And yeah, there is also like a quite a lot uh, of things of you can do on top of that. All right. So lastly, the thing I wanted to just demonstrate you how you can quick start with Noir, Garaga, Cairo, and Starknet. So this is the repo I will share afterwards. So it contains a project called Scaffold Garaga. And this is essentially a tutorial, like a three-step tutorial where you go from creating a really simple Ziggy circuit, and then just gradually you increase the complexity, add in the states, add in more involved logic, and finally deploying to public Starknet testnet. And given the timeline, so now we will do just the first step, and yeah, I encourage you to complete the tutorial afterwards, unless you already did that. So this is the repo, and yeah, so the way it's organized is you have several branches, and essentially every step is another branch. So in order to kind of move to the next step, you have to check out to the following branch, and this is described in the README. And also for every branch, you have a makefile with the commands. So you have the shortcuts for all the like scripts and commands that you might need in order to generate contracts, build circuits, build contracts, deploy, declare, etc., etc. Right. So what I'm going to do right now is I'm going to switch to the terminal.
Sorry, sorry, Michael, can you hear me? Yeah, right.
Yep.
Something happened with my Zoom. There's a couple questions if I can ask you before you go to the next part.
Yeah, of course.
Perfect. So, all right, Augusto, you don't have a Telegram, only Discord. It's perfect. Don't worry. I'm sending you emails with all the presentations, recordings, and everything. And you can also find, I recommend that you get a Telegram because you can ask questions in there to the mentors, right? So you can, for example, tag Michael and ask a question, Augusto. So I would recommend using Telegram. But if you don't want to get a Telegram, it's also okay. I'm sending you an email that you have been receiving if you register in the hackathon. Let me know if you haven't, but you should be receiving an email with all the resources. Otherwise, you can find them in the dev post page. Let me send you the link right now. But you will find there all the resources for the hackathon. Here they are, and let me send them another link here that I have. There you will be able to see all the resources from all the workshops that we have had and the documentations and everything that you need. And also I'm sharing right now a YouTube link to a playlist with all the workshops. So you will find Michael's workshop in there, Fat Solutions, if you're interested in privacy, and the other workshops, right? Okay, so you will find there. Celia, can we have the presentation slides? Michael, can we have the presentation slides?
Yeah, of course. Yeah, I'll share everything after the call, and
Perfect.
yeah, you
I will
can.
send it to you guys. I will send it to you, Celia. I will send it in as an email, and you will find it in the resources channel too. Then with DeFi, can we hide the transaction value?
Sorry, could you repeat
Yes.
that?
Can we hide the transaction value in DeFi? If, Mhm.
Yeah, I mean, so as I said before, right? So we now have two solutions that you can use. So if you wanted to just
Mhm.
hide the transaction value, And for instance, like you do not necessarily need to high sender receiver. You can use confidential tokens. This is something that Fat Solutions provides. So it's a framework called Tongo, and you can look at that. Or I think so. They probably have covered that on the workshop. So this works for use cases where, I don't know, imagine that you have a relationship between the employer and the employee, or the supplier and like a merchandise. So their kind of connection is not private. This, like, everyone knows that I know, like, I'm employee of StarkWare, but I would really wanted to hide the, like, the amount of the payout that they do to me, right? So this is the example of the use case where confidential tokens are enough, are good enough solution for the problem.
Perfect. Okay, Celia, let me know if there's further questions on this. And Michael, there's another question here in the chat. So Laura is mentioning that give me a second, I'm looking for them. Laura mentioned that she is building a diffusion AI model with Python. And
Mhm.
the question is, what could be a good workflow to run a diffusion LLM model or a diffusion or LLM model inside a hint and get proof of the outputs?
Okay, so let me try to find it. So we have a yep. So if you wanted to do verifiable machine learning on Starknet, so the way to go, I mean, I would recommend to use Luminaire. So this is a framework developed by Giza, and it uses the prover by StarkWare, and it's built specifically for doing verifiable AI, and I think so they're now using it for the rect um, media, like to provide the algorithmic feeds. So yeah, that's quite cool, and I think they have certain, yeah, certain primitives that they provide. I'm not sure if it's like already compatible with the Onyx standard. So that's probably not, yeah, not yet available, but you can just like explore and see if it's something that you can leverage. Yeah, I would do that. And secondly, so the same company uses, they also have another framework, also in Cairo, that should work with the like a certain simple models. So that might also work for you. So if you don't mind, I will share afterwards. Or Omar, you probably also know the, yeah, so where to get the links.
Yes, so as particularly you want to send the link to the GISA open source repo, right?
Yeah.
Oh, okay, I look for it, don't worry.
Thanks. Okay,
Uh, uh,
so
Sorry, Michael, sorry. So suppose that Laura doesn't want to use or GISA, or GISA is not useful for what she's looking for. What would be the second best option for her to do
you mean to
this?
do the verifiable? I mean, like,
Yes. Mhm.
okay, so uh, that's a really good question. So, uh, like, as a hackathon project, I think it doesn't really. I mean, like, doing
It's too
this from
much.
scratch in Cairo would be like really involved. So I would really recommend
Hmm. Okay.
using any of the existing frameworks.
Mhm.
Yeah.
Okay, okay. Perfect. Yeah, it could be too hard, Laura. All right. Okay. Thank you, Michael.
Okay. So right, let me quickly do an overview of the repo, so that you have a basic idea how to work with it. So in this repo, I have three components. So first is the circuit. This is these ZK program that we run on the client side. Second is the contract, the smart contract part that is executed within Starknet. And lastly, this is the application, the interface that interacts with like both interacts with the zero knowledge program that is executed on the client and also with the contract that is deployed on Starknet. And we start always with this circuit. So everything starts with the circuits. So this is a Noir project. For the first step, this is a really like a dummy program that does nothing, just asserts that the two inputs are not equal. So note that we have one single private input and one public. Next, we have the contract. So this part is like a fully code generated. So there are no manual work here. So it is generated based on the circuit that we have here. And lastly, we have an app that provides just a simple interface, a single page where you can track the states, like what is your application is doing right now. All right. Now I'm just gonna quickly go over the steps. So first thing, right, that we need to do when we have our circuit written is we can build it. Build the circuits. Okay. Next is what we have to do is we have to generate the verification key for the circuit. So verification key is something that is necessary to like firstly generate the verifier, and like ultimately this is the uh, like a certain data that lives on chain that is required to verify all the subsequent proofs that you produce on the client side. So we generate the key. After we generate the key, we can generate the verification contract. So here's where we use the Garaga for the first time, right? So we say, okay, so here's our project. So we point Garaga to the verification key that we just produced, right? And we also specify the proven system that we use. This is the default. And we also say that this is going to be like the project name for the verification contract, right? And this is what Garaga produces, right? So it just generates everything you need in order to compile like a fully fledged smart contract. It's a Scarp project. Scarp is like cargo and Rust, but for Cairo. And here you have the files for the smart contracts. And now we can actually build the. I'm sorry. We can build the contract to ensure that it is correct. And everything is good. Now, for testing purposes, right? So before we go to the Starknet public network, we can use a local development network that is really handy if you just wanted to, debug smart contracts. And there is already in Alice like a command that would spawn local Starknet nodes with these several pre-existing accounts with balances that you can use for deploying and interacting with contracts. Yeah, so I have started the development network in a separate tab. I return back, and now I wanted to deploy my verifier contract to this local development network. And on Starknet, it's typically done in two steps. So first, you have to do something that is called declare. So declare is as if you upload your codes so that you can later instantiate it. And I do the declaration. It would, again, recompile the contracts, and then it would upload the code, the hash of the code to the network. Yep. So once it's done, we can do the deployments. So in other words, we have instantiated the contract that was previously declared by us. Okay, and we can do this multiple times, like as many times as we want. Now, this is essentially what you all you have to do for the first step, right? So now we have the verifier in our local development network, so we can produce the proof on the client and try to verify it. Okay, and the application, like the web application that is available for the basic step, does exactly that. So, and I will just run it and switch back. So here's like how it looks like. So it's a single page, really simple. Here we have the inputs, right? So recalling that those are the two inputs that we have in our circuit, like the X and Y. And yeah, I just press the button and we generate the witness, like inputs for the circuits, then we produce the proof, then we encode the proof with the call data, encode the proof with the Garaga to produce the call data for our contract. This step we are currently skipping because we interact with the local development network. And finally, we send the transaction. So for the kind of first step, we do not actually send the transaction. We just invoke the contract. So we call something that is called view method, which does not produce the actual transaction on chain, but we have invoked the contract that lives on chain, right? And so just to show that it works. Oh yeah. So it will fail on the very first stage just because the inputs do not satisfy the constraints, right? Because we yeah. So this is the constraint that is not satisfied. Right. So this was the first step. After that, there are examples how you add more involved logic to the circuits, and then how you introduce some notion of state, what we mentioned before, on chain. And final step is how you put everything together, deploy to the public testnet, and then interact with the contract through the wallets, right? Where you actually need to sign the transaction and send it on chain. So everything is here. I encourage you to try it. And yeah, let me know if it works or does not work. Thank you. Yeah, if you have any questions, please ask. So I will share all the links to the slides and the repo, and yeah, that's pretty much it.
Thank you. Thank you very much, Michael. Thank you very much. I see that. Oh, can you share the link to the GitHub repo, please, Michael? And
Yes, sharing this right now.
perfect, perfect.
Okay.
And also, let me just a second. All right, Michael already sent it. And yes, I see that Laura SC are talking about maybe making a team. Cool. Uh, okay, I think we are done with questions right now. All right, I think we are all right with questions. Guys, please, if you have further questions, go into Telegram. I know that some of you might not have Telegram. If you don't have Telegram, send me an email, please. Send me an email and I can send your questions in Telegram. My email is Omar. I will write it in the chat, but it's Omar at starknet.org. Omar at starknet.org. You can find also my email in the post webpage. You can send me any question that you have. Again, preferably you can go to Telegram and there you can ask questions to Michael directly there. What else? Okay, I see that Michael is answering a question already here. All right, I will also write my handle in Telegram, Espejelomar. I wrote it right now, Espejelomar, and I will send the repo. Oh, you answered it already, right? Okay, so just
Yes.
for perfect. Okay.
Yeah,
Yes.
I can
Mhm.
so like the question was, is Garaga like supporting only ultra honk proofs? So yes, this is what Garaga supports right now by default. So it has two flavors. So one is the default one that is used by Aztec, but there's also the Starknet flavor, which is the like a really high level. So it uses a different hash function and allows you more cheap verification on Starknet. So if you wanted to verify the proofs cheaper, you use the Ultra Starknet honk. If you just wanted to be, like compatible with the default, you use Ultra Ketchup honk. So
All right. Thank you very much. Thank you, OXN. Thank you, Michael. Everyone, please go into Telegram, ask as many questions as you want. And well, I think you're ready for the privacy track. We're missing the WhatsApp workshop, but you know everything you need to know with Garaga and Noir. So thank you. Thank you very much, Michael, for your time, for the sponsorship, and see you very soon.
thank you for hosting. Good luck, everyone.